Hi, welcome back to Unit 2 Dynamics here in AP Physics 1. So this video is going to focus on tension and equilibrium. We've talked a little bit about tension equilibrium, because this is when we talk about balanced forces, right? So when there's no acceleration, okay? And so this is very important for tension, because oftentimes these are problems where you're like hanging something and you don't want that object to be accelerated at all. It's also what happens in beams and bridges and so forth. You don't want acceleration there, okay? So tension is defined as the force exerted by a string, rope, or wire that is pulled tight. And so basically, the way to think about it is, if I have, like, let's say, an object hanging off of a string attached to a ceiling, okay, tension is in the string, okay, and it points towards, so if I'm doing a free body diagram, it's going to point towards what is really causing the tension. So with the ball, the string is pulled tight, yes, because of the ball, but also because of that connection point at the top. And if I look at the ceiling, and I'm doing a free body diagram there, the tension is going to point down, because what's causing the tension at the ceiling? Well, it's going to be really the weight of the ball, right? But the thing is, right, those tensions are going to be the same, right? It's going to be the same tension throughout the string. And that's because all of our strings here in AP Physics 1 are going to be assumed to be, I don't know why it's not it. Okay, all of our strings are going to be assumed to be ideal. And what does that mean? That it's massless, frictionless string. So oftentimes in lab settings, teachers will use fishing line, because fishing line is nearly massless. Like, if you only take a little bit of it, it's got maybe a gram worth of mass, right? So we just consider that to be ideal. Okay. Now, for simplicity, again, unless otherwise stated, all of our ropes, strings, cables, and so forth are going to be assumed to be ideal. Okay. And so this right here, I forgot to point this out, but this bullet point here shows that fact that the tension is going to be the same throughout. The string just transmits the force from one location to another. Now, remember, we said that objects are going to be in equilibrium when the net force acting on it is zero, right? It's not when there is zero force on it, but when there is a net force of zero, okay? Remember, there's always forces acting on objects. It's just that how are those forces acting? Are they causing acceleration, or are they causing zero acceleration? So here's a quick little example, just kind of more of a conceptual type. So here we have two cases. You can see one case where the gentleman is pulling the bucket up, right? And the other where the bucket is being held by two strings. And we're asked, is the tension in the rope in case 2 greater than, less than, or equal to the tension in rope 1? Okay. So to think about it, we're going to draw free body diagrams about really, the points of contact here. Okay. And so for rope 1, I've got the tension up, right, or around the points of contact for the bucket is what I should say, right? And I've got the weight of the bucket down. And so what does that tell me? That T1 equals Fg, which equals mg. Okay. Now we look at the point of contact, or the bucket, right, for the second one. So I've got Fg down, and then I have these T2s. Now, remember, these T2s are going to be equal because we talk about this as an ideal rope. And so if I sum the forces, I end up with 2T2 minus Fg equals 0, which tells me that T2 is going to be Fg divided by 2, right? Because I add Fg over, and then I divide by 2. So what does that tell me? That tells me the tension in rope 2 is going to be less than that of the tension in rope 1. Why? Because in case one, it's the string is only attached at one point, and then in the other, it's attached at 2 points. Okay, so it's like evenly distributing the weight of the bucket. Okay, so let's look at an example, right? A little bit further of an example. So you got a 1.84 kilogram bag of clothespins hanging in the middle of a clothesline, causing it to sag by an angle of 3.5 degrees. Find the tension force in each part of the clothesline. Okay, so basically, here's my picture, and it's telling us that if I put this all the way through, right, it tells me that this is going to sag at 3.5 degrees, and that has 1.84 kilograms. So if I remember our process, draw, sum, solve. Okay, so first step, draw the free body diagram. So we're going to look at the point of contact, which is right here. So what forces are acting at that point? Well, we have the weight of the clothespin bag, and then we have the tension in the string, right? Now, because this is, right, because it says it makes an angle, right, of 3.5 degrees, the tensions are going to be equal. Ultimately, in the end, the tensions are going to be equal. So the only time they won't be equal is if the angle differs. So if I have one going like this and one string going like this, where the angle is definitely different, right? So if I'm hanging something here and I've got one attached like that and then one kind of attached like that, okay? Now you'd have to separate this into T1 and T2, right? Because these angles, or whichever angles you're looking at, are going to be different, okay? So you have to be, in this case, right, it's telling us that it's going to make an angle of 3.5 degrees. And this idea of middle means when I put it there, it's going to hang down nice and evenly, right? So there's our draw step. Now our sum step. Okay, so sum the forces in each direction. So the net force in the x direction is equal to 0. The net force in the y direction is equal to 0. So in the x direction, right, I'm going to have to break this up into components. Now, what you're about to see, don't do this on the AP test. Okay, so I'm going to have Tx here. Okay, remember on the AP test, if you draw the components, they're going to not give you points because those should not be drawn on your, not drawn on the free body diagram. Okay, but so I split up Tx and Ty into components. So I'm going to say I have Tx, right? I have a positive Tx, I have a negative Tx, and that's going to equal 0. Okay, well, that's just telling me that Tx equals Tx, which doesn't really help, which is, again, T cosine theta equals T cosine theta. Well, same angles, those go away. It just tells me T equals T, right? So there's your mathematical proof that tension equals tension, right? Now, where we're going to find it is the y direction, because in the y direction, we have the added force of the weight. Okay, so we're going to have Ty plus Ty minus Fg, and that's going to equal to 0. So this basically tells me I have 2 Ty minus Fg equals 0. So 2 Ty equals Fg, right? I'm just doing my algebra. Remember, physics stops at this point, and math takes over down here. Now we've moved in, so these are our sum step, and now we've moved into our solve step. Okay, sorry, I should have distinguished the motion, right, the movement from one step to the other. Okay, so Ty is going to be Fg divided by 2. But what is Ty? Ty is T sine theta, right, because it's our opposite side to our angle. And so it's going to be Fg divided by 2. And so T is going to be Fg over 2 sine theta. Okay, so now we can just plug in numbers, or we can simplify one more step. We got mg over 2 sine theta. So T is going to be m, which is 1.84, times 9.8 divided by 2 sine 3.5, right, our angle. And that's going to give us a tension of 148 newtons. Okay, so that's going to be the tension that is what's happening, right, in this, once we kind of split that string into two. So yes, when you do tension problems, it is a single string, but Once you kind of start adding pieces to cause tensions to happen, then it becomes, you treat it as two separate strings. Okay. All right. So the next video is going to center around, we're going to start talking about friction, which is going to be a big topic here in